Conservative fields, potential functions, path independence, and then this last one over here, well, second to last one, if C is a closed curve, then and F is conservative, then according to the fundamental theorem of line integrals, it's just going to be the potential function evaluated at the endpoints. But if it's a closed curve, then the endpoints are the same, right? Does that make sense? So it's like saying from something to that same thing, and you're subtracting it. So, so all this is related to, I think we call it the fundamental theorem of line integrals. Isn't that what we called it? Right? Which is straight off of the fundamental theorem of calculus. So, fundamental theorem of line integrals kind of revolves around this idea, or these ideas of the vector field being conservative. If it's a conservative, then it's a gradient field. If it's a gradient field, then we can find a potential function, etc. So line integral over closed or over a curve C. Now instead of just putting F like it's written usually, if F is a conservative field, then it's actually can be represented as the gradient of some potential function. Remember that gradient is a vector, so we're going to dot it with the arc length, or the arc, or the tangent component. Then this is equal to f of b. Well, I don't know if I should call it b, but I think we called it r of b minus f of r of a, where this is a start point and this is the end point. So the idea is to basically find the antiderivative, well, find the potential function. Potential function is kind of like the antiderivative of the gradient field. And then use that to evaluate at the endpoints, which is more or less what we did in the fundamental theorem of calculus. Except the original fundamental theorem of calculus, we're just dealing with nice scalar functions. And here we're dealing with gradient vector fields. Okay? Yeah? For the path integral, we put in a scalar function. Well, it's a scalar function. We don't dot it anymore. So a path integral takes a function from R2 to R, or I guess it could be R3. We'll just put R2 to R. And then you're integrating of f dr. Now, a couple things to note here. The f is not a vector field, and the dr is not a vector. It's magnitude of the parameterization. a line integral, takes a vector field and then integrates it over a curve. And so this is going to be the integral from a to b of f of r of t. And you have to dot it with the derivative component dt. So if you can continue to remind yourself of the difference between a path integral and a line integral, then that would be good. Now, so all this stuff works for the fundamental theorem of line integrals if your f is conservative. But now we're going to focus on slightly a different type of line integral. We're going to talk about line integral over closed curves that may or may not be path independent or conservative or gradient fields. Okay, so this is from last time, and then today we're going to continue talking about line integrals, but line integrals over closed. Yeah. This is 16.4. So the title of this section is called Green's Theorem. All right, so I'm going to steal Green's theorem from my notes, which was stolen from the book. And what this does is it does an interesting thing that we'll be seeing a lot. There's going to be a theme to this with all the theorems that we're going to cover. So C is a positively oriented, piecewise simple closed curve. So there's a lot of adjectives. Closed, basically closed. Piecewise smooth means it's differentiable in pieces. So you could possibly have a nice circular curve or a nice triangular curve that can be done in pieces, or anything that, as long as it's smooth in different pieces, then that would be fine to use as a simple piecewise closed curve. Now, positively oriented, because for line integrals I mentioned that the direction of the curve is important. On a closed curve we have to talk about a positively oriented curve. So positive orientation is going to be counterclockwise. Now, for a two-dimensional curve, that's easy enough to identify. it's a closed curve, so you should think about a closed curve as when they say positively oriented, you just imagine that curve going around in a counterclockwise direction. So for any of these examples over here, the idea of counterclockwise seems pretty clear. And for something that's a little bit more difficult to identify, it still should be able to figure out which way the counterclockwise direction should go, right? As long as you know what the area is on the inside. So closed curve says you have an inside and an outside area. Remember those paint programs where you have a little bucket of paint you pour into something? If it's a closed curve, you pour into something and it's going to enclose, it's going to color whatever that is. If for some reason you didn't close the curve, you click on that little area, but if you didn't close it, then everything is going to turn into whatever color you change it into. So it's important to be able to identify what your closed curve is and what the area is inside the closed curve. And then from there you can figure out what the counterclockwise direction means. Another way to describe it is that if you yourself were walking along this counterclockwise direction on this curve, on this closed curve, then the inside would be on your left side. Think about that. All right, so we have C is a positively oriented, piecewise, simple, closed curve on the plane D, and in the region C is bounded by, and let D be the region bounded by C. So what we want to do is we want to just identify a region just to say that I'm going to want the function P and Q to be continuous in that domain. So when we talk about a domain, we talk about a two-dimensional region, and we just want to make sure that the functions P and Q are continuous and differentiable on that region that contains the curve, the closed curve that we're talking about. So then, this is a statement of the proof here. Then we say that the line integral remember that the line integral has this form. I usually write integral of C, integral over C of f dotted with dr. Remember that that can also be rewritten as p dx plus q dy if we allow our f to equal p and q. Then this is another way to express your line integral. And what we're saying is that this line integral is actually equal to this double integral. And that's kind of like a big deal, where we can let one integral equal to another type of integral. So what's the relation between them? The relation between them is that, well, D is the region bounded by that. So D is going to be the region that's bounded by that closed curve. So another important aspect to note here is that C is a curve and it's the boundary of the region, the two-dimensional region D. And then inside of this is some weird partial of Q with respect to X minus the partial of P with respect to Y. All right, well, I'm not going to go through a complicated proof because it could get complicated. And so I just want to do a couple of examples to show you how the Green's theorem works. So I think I might have some in my notes. Okay, so these first types of problems are asking us to, oh, by the way, I don't know if you can see this notation, but they have a they have a new kind of notation for closed curves, integrating over closed curves. Let's do number 2. Uh-oh. Let's do number 1. No. I don't know. They're both kind of hard. The instructions say to compute this line integral directly. So let's do it directly just to get us some practice for doing line integrals. They're saying that we want to compute this line integral where C is a circle with a center at the origin and a radius 2. And usually one of the first things we want to do is we want to try to figure out how to represent C in terms of a parameterization, right? So let's do that. Let's try to find our parameterization. R of T is a circle of radius 2. Now, they should have mentioned whether this is going in the clockwise or counterclockwise direction, but let's just say it's going to go in a counterclockwise direction. And then you have radius 2. So the circle is going to be the cosine and sine combination. So that's cosine of t and then 2 sine t. And then we're going to let t go from 0 to 2 pi. So the other thing we need is to find the derivative. So our derivative of cosine is negative sine, and derivative of sine is positive cosine, and the two constants are still there. So if we want to pick this and put it directly into this line integral of this form, we just replace the x's with the x's and replace the y's with the y's. And then we're going to replace the dx and dy with these derivatives that we just found. So, and we're going to integrate this from 0 to 2 pi. So we can write it directly into this single integral. And we got x is 2 cosine t minus 2 sine t times dx, negative 2 sine t, plus, and then we have x plus y, so 2 cosine t plus 2 sine t, and then our dy is 2 cosine t dt. That turned out to be kind of long, but this is your x minus y dx plus x plus y dy. So if we continue working on this, we should hopefully be able to simplify this a little bit at least. We've got a negative 2 cosine t sine t minus minus, I'll make this a 4, and then minus minus a 4 sine squared t plus another 4 cosine squared t plus 4 sine t cosine t. Oh, that's not too bad. We got sine squared and cosine squared, and we got these two things to be opposites of each other. So that's just a 4, right? Wow, that was easy. 0, 2 pi, and then 4 times 1. So this is 4 times 2 pi, which is 8 pi. That wasn't too bad. Yeah.
When you make the assumption that it's positively oriented, how come we're not integrating from 0 to negative, like make it go counterclockwise? Or I don't know.
No, counterclockwise is the 0 to 2 pi direction.
Oh, right.
Yeah.
Yeah, the negative.
Yeah.
Subtraction.
Okay. Now let's do this using. Should we continue on this page? Let's continue on this page using Green's theorem. I use this color. What we want to do is we want to make this into a double integral, right? So for a double integral, we need to find the region. First of all, we need dq dx partial minus dp dy, because that's what's going to go inside of our integrand, right? Of your double integral. So the derivative of the second one with respect to x, well, that's just 1. The derivative of the first function with respect to y, that's negative 1. So that's just 2. And now the region is a circle of radius 2, right? This is the inside. And so for this one, I'd rather go straight into polar coordinates and say r is going to go from 0 to 2, and theta is going to go from 0 to 2 pi. Okay? So according to Green's, my integral p dx plus q dy over c is equal to a double integral over our new domain of 2 dA. And so since I'm going to go into polar coordinates, I'm going to, the 2 is a constant, so I'll just move it out. And then r is going to be integrated from 0 to 2. And then theta is going to be integrated from 0 to 2 pi. And don't forget the r. And so I can split this up to 2 integrals. I have an integral from 0 to 2 pi of d theta, and then an integral from 0 to 2 of r dr. Now the integral of d theta is just theta going from 0 to 2 pi. That's just going to be 2 pi. And then I have r squared over 2 from 0 to 2. So I think if I just put 2 in there, I'm going to get 4 over 2, which is 2. Which gives me 8 pi. So I don't know which one was easier. But in a lot of cases, you'll find these things where one of these integrals might be easier than the other. So it's usually the double integral turns out to be a little bit easier than the line integral. But that's usually the case, not always. Ash, do you have a question?
I was saying, at least for this one, you can also kind of do geometrically.
Yeah.
You can see it's 2 times the area.
Yeah, it's 2 times the area of the circle, which is another interesting thing that we should begin to do a little bit more. Taking it from here, say. So I'm going to ask you to do this a little bit more often later on, especially when we start dealing with difficult integrals. If the constant that if the thing that goes inside your integrand happens to be constant, you can always take that out. And when you're able to take that out, then you have a double integral where the integrand is 1, right? You remember what that was? Say from the exam? It's the area under a surface. The surface is a plane 1. Numerically, it gives you the area of D. So this is 2 times the area of D, which D is a circle radius too, so pi r squared business. Okay? So that's another thing to start thinking about. So we're going to start throwing a bunch of different ideas with these integrals and relating different types of integrals. And then we're going to need as many of these tricks as possible for us to be able to compute these integrals to try to get to the answer. All right, let's do another example. So let's do, I don't know, 2 or 3 or 4. Any suggestions? Four? Hmm. Yeah. Yeah. So if C happens to be a negatively oriented curve, which means it goes clockwise, then it would just be the negative. So that's the difference between a positively oriented and negatively oriented curve. And there might be some times where, maybe not so much for Green's theorem, but there might be some time where you're dealing with another theorem and then you have to orient your, whatever it is you're trying to draw a certain way, and it turns out to be more difficult to try to orient it the correct way, then you just say that your orientation is negative and you just throw a negative sign in front of it. So we'll see more about orientations later on. So here consists of an arc of the parabola y is equal to x squared from 0, 0 to 1, 1. So let's begin to draw this region, or this curve. Remember, as a line integral, we're looking at a closed curve. Or as a line integral with a little circle on it, we're looking at a closed curve. So this is a piece of the parabola from 0, 0 to 1, 1. And then the line segments from 1, 1 to 0, 1. 0, 1 is here, right? So this line segment from here to here. And then from 0, 1 to 0, 0. And then you want to just, when you're drawing this out, you should be able to show that this is a positive orientation, which is going counterclockwise. And exactly the way they described it there, looks like, in fact, it is going counterclockwise. So we can identify the region inside when we eventually think about using Green's theorem. But let's approach this using the instructions that they have, which is to compute this line integral as a line integral directly first, and then see if you can compute this line integral using Green's theorem, and that means changing your line integral into a double integral. Okay, we'll do that second. Let's first do the line integral as a line integral. Now, there's a few things going on here. First of all, this curve, quote, curve, is a piecewise smooth curve, and it comes in 3 pieces. We can call this C1, C2, and C3. And so what we would have to do is we would have to find a line integral of each of these curves separately, and then add them together. Okay? Already I'm not liking this, but let's go through it. So your line integral is going to equal to the line integral over C1 plus the line integral over C2 plus the line integral over C3. By the way, this drawing of this curve, this integral with a circle in it, they often use a little arrow to show the orientation, show that this is a positively oriented curve. It's just saying that it's a closed curve. Yeah. Yeah, they're special. So whenever you're dealing with a closed curve, your line integral will have this circle in it. You're discovering more new cool symbols in math, huh? Anyways, we have to do 3 of these. And so let's parameterize each of them. So C1, let's call it R1 of t, and that's going to be the parabola. Now it's going to go from 0 to 1, and if you let the t equal x, and then your y is just going to equal x squared, which is t squared. Then this is your first parameterization. We can go ahead and do this line integral, but we also need the derivative. So r1 prime of t is equal to 1 and 2t. And so if we take a look at our integral with c1, this is going to be the integral from 0 to 1. Now x is equal to t, y is equal to t squared, and the dx is equal to 1. So that's the first component of your line integral. The second component, x is equal to t, y is equal to t squared, and dy is going to equal to 2t. And then you can simplify this and then compute it. I think this simplifies to t to the 6 plus 2t to the 4th and then if you integrate this from 0 to 1, this will just be t to the 7th over 7 plus 2t to the 5th over 5. And so that's 1/7 plus 2/5, which is 19 over 35. So that's 1. Okay. Now let's do C2. So this is where you get the practice parameterization. Now C2, remember, it's when you're doing line segment, you start with the first one and then the direction vector, the second one, and stuff like that. So I'm starting with the 0.11. So maybe I'll write it like this first: the 0.11 plus t times the direction vector. And the direction vector goes from it's a vector that goes from here to here. So it goes from 1, 1 to 0, 1, which means it doesn't move along in the y-axis, and then it moves to -1 direction in the x-axis. So that simplifies to 1 minus t, comma 1. And if you want to put 0 and 1 in there to make sure that you start and end at the appropriate spots. If you put 0 in there, you're going to get 1, 1. If you put 1 in there, you're going to get 0, 1, which is exactly the starting and ending points. All right, so the prime, the derivative is, where is this function? It's -1, comma 0. So that's good news for the dy. The dy is going to be 0, so that's going to disappear. All right, let's find our integral for C2. Integral from 0 to 1 of x. X is 1 minus t. Now we've got to square that. Y is just 1. And dx looks like it's -1. And the dy is equal to 0, so the second term actually wouldn't matter so much because it'll disappear because we have a dy of 0. So we just need to worry about this thing. Looks like we could just FOIL that out. Add t squared minus 2t plus 1, and with a negative in front. And then we integrate that. 1/2 or 1/3 t cubed plus t squared plus t evaluated from 0 to 1 with a negative in front. So that's a 1/3 plus 1 plus 1. Wait, is it a plus 1? Sorry, going too quick here. The middle term's negative, right? Because there's a minus sign in between. I hope that's right. Is that right? Should I punch it in Wolfram Alpha just to make sure? We got one more. So if we follow the same rules as we did over here, it looks like our x is going to be, or y is going to be 0 the whole time, and then your x is going to go from 1 to 0, so I think that's a 1 minus t again. Okay, so I'm kind of doing this part quickly, where you have to parameterize a line segment. You're going from one point to the other. You guys need to know how to do that. And there's a formula in the book that shows you how to do that. It's like the starting point plus the end point minus the starting point times t, or something like that. It's really important that you should be able to parameterize that. And if I put t is equal to 1 or t is equal to 0, I'm going to get 1, 0, which is where I want to start. And if I put t is equal to 1, I'm going to get 0, 0, which is where I end. And so that looks like it's the correct parameterization. Yeah?
This is kind of a weird conversation graph, but you don't have to parameterize it from t to 0 to 1, right? You could do something weird and parameterize it from 0 to 2, scalar multiply.
Yeah, yeah.
It's the same either way. Right?
Yes, yes. But parameterizing a line, if you do it this way, your t limits are always going to be 0 to 1 instead of scaling it. Yeah? I don't know. Should it be the other way around? Yeah. I was just checking to see if you guys were paying attention. X is going to be 0 the whole time, and then y changes from 1 to 0. Thank you. All right, and so the derivative, again, is going to be 0, comma, negative 1. So that gives you your dx and dy component. So your integral here for C3 is going to be, these are closed. Actually, I'm sorry, these are just line integrals without the circle. Oh yeah, I should take the circles out. Anyways, we're going to go from 0 to 1. The first one is going to have a dx, so instead of putting in those values, I'm going to put a star times 0, because the dx is equal to 0. And then the y part is x times y dy. So x is equal to 0. Oh, that's also equal to 0. Y, and then negative 1. So you have an integral here, a definite integral, that's equal to 0, so this whole thing must equal to 0. All right, let's see if we can summarize this. C1 plus C2 plus C3 should equal to 19 over 35 plus negative 1/3 plus 0. Can we do this quickly in our heads? 19 times 3 plus 35. Oh, we're subtracting too. Ah. 30, 40, 50, 57 minus 35. What? 22. Okay. So, as you can see, if you have this piecewise smooth closed curve, each of those pieces would require its own line integral. So if you put it all together and notice that it is in fact going to be a closed curve, then we could just focus on the boundary and maybe take that boundary to be our, take the double integral for that boundary. So that's what we're going to do. Let's redo this using Green's theorem. And I'm going to keep this picture. And then use the formula. So we need the partial of q over partial x minus the partial of p over the partial y. We got our p and q. I want to take the derivative of q with respect to x. So x is a variable, y is a constant. And then I want to take the derivative of p with respect to y. So that's 2x squared y. So 2y, and then the x squared is a constant. So this is going to be my integrand. Now I want to do a double integral, and it doesn't look like I need to change this into polar or anything like that. And it looks like it doesn't really matter which way I want to integrate first, except if I integrate with respect to y first, I would go from this graph to 1. So what if I integrate with respect to x first? If I integrate with respect to x first, I'm going to go 0 to a function. So I think that might be a little easier. So let's integrate with respect to x first, and then integrate with respect to y last. And then y just goes from 0 to 1, so I know that's constants. So the only thing I need to do is I need to figure out what this graph is. This graph is y is equal to x squared, but I want it as a function of x, or as a function of y. X is a function of y. So that's going to be the square root of y. So that's it. There's my double integral. I'm going to integrate the inside. First of all, my function is y minus 2x squared y. And then I'll integrate with respect to x first, going from 0 to square root of y. And then I'll integrate with respect to y, going from 0 to 1. I don't know if this looks any easier, but hopefully it does. We go inside the inside integral first. Integrate with respect to x. This is xy minus, this is 2, this is going to be x cubed over 3. And then I need to evaluate this from 0 to square root of y. These are my x values. So that's going to give me square root of y times y minus 2 square root of y cubed over 3 times y. So we can write this a little bit better, yeah? Y to the 3 halves minus 2/3 y to the 3 halves plus 1, 5 halves. And now let's integrate that from 0 to 1. Did I switch? No. So this is going to be y to the 5 halves over 5 halves minus 2/3 y to the 7 halves over 7 halves, evaluated from 0 to 1. Whew. All these fractions. 2/5 minus 4 over 21. What's this equal to? What is it, 22? Over 105. Cool. Okay. Any questions? So I had this idea of giving you some work to do to see how it'll work out. This is not a quiz. This is just a worksheet that maybe you guys could try doing these problems. And I have one more. In the past, I've had honor students come and do a class lesson, but the honor students are going to be doing something different this year. So when they do the lesson, they would talk and present the material for about half an hour or so, and then they would hand out a worksheet to do, and you guys work on it. And in a group, together, whatever. And then we'll come around and give you guys a hand. So, the first set of questions is just asking if you can use Green's theorem or not. Really, what you need to look at is the curve to make sure it's not closed, or if it is closed, you can use it. If it's not closed, you can't. The more interesting problem, since we only have 10 minutes left, I thought I was going to cut this off and you guys would have 20 minutes to work on it. Since we only have 10 minutes left, I asked you to pick one of the 3 bottom ones where you actually have to do a Green's theorem calculation. So why don't you do that? In about 5 minutes, I'll check up and see what you guys are doing. So do one of the bottom 3 problems.